Hello everyone, welcome to lecture 51 of the course Diffusion in Solids. So, in the last lecture of the previous weeks, the lecture before the tutorial, we were talking about the diffusion aspects in the metallic alloys, where we talked primarily about the diffusion of interstitial solutes, and we also talked about the self-diffusion features in metals. So, we will continue discussing metallic alloys and talk about the impurity diffusion, the dissociative mechanisms, and starting with a little bit about the solid solutions and the Hume-Rothery rules. So, we know from perhaps some of you have done physical metallurgy courses where we see that the solid solutions are a homogeneous mixture of two or more types of atoms in the solid state. So, we saw the thermodynamics of it when we revisited, and primarily they occur two types. One is interstitial solid solution, another is substitutional solid solution. So, as the name suggests, interstitial solid solutions are the ones where atoms occupy the interstitial spaces. This we have known before, and for this to form, the solid atoms must be small, typically less than 0.6 times the solvent atom size, and the most common interstitial solutes are carbon, nitrogen, hydrogen, and oxygen, but it is no way an exhaustive. There are more cases where elements act as interstitial solutes. Ultimately, it is the relative ratios between the solute and the solvent. For example, transition metals are more soluble to interstitial atoms due to their incomplete electronic shells. So, here they can dissolve more of these interstitial elements, and the interstitial solutes diffuse by jumping between the interstitial positions, which can also impact the solvent's properties. The classic example of the interstitial solid solutions are steels. That means you have austenite, you have ferrite, where carbon is dissolved. Carbon occupies an octahedral interstitial site in this BCC structure. So, this is the octahedral void, and there is a limited solubility because the incorporation here causes a strain between carbon and iron. You can see that carbon atom diameter is 0.15 nanometer, whereas the interstitial size site in the BCC iron is 0.0385 nanometer. So, there is a lot of distortion that happens even though you call the carbon as a smaller atom. Carbon in gamma iron, it occupies the octahedral interstitial sites in the FCC structure, which is indicated here. This is the octahedral site, this is the octahedral site, and higher solubility as compared to alpha iron due to larger and more symmetrical interstitial spaces in FCC. So, these are the radius ratios for various octahedral and tetrahedral site. This we also saw briefly in when we were talking about the structure and the defects. This is an activity question for you. Why does carbon prefer octahedral sites in both BCC and FCC iron, even though tetrahedral sites are larger in BCC? So, if you see here, the tetrahedral sites in BCC are 0.291 R. That R is the radius of the parent atom, whereas FCC it is 2.225 R. Still, the carbon prefers, or rather, if you compare in BCC, then octahedral site radius is 0.155 R, which is much smaller than the tetrahedral site, but it still prefers an octahedral interstitial site. So, maybe an activity question for you to work out. Then the substitutional solids solutions are the where the solute atoms replace the solvent atoms from its regular crystal lattice. A host of examples exist like brass, alloy of copper and zinc, where zinc replaces some of the copper atoms. But the thing is that when we talk about the solubility, then solubility is not that any amount of solute you put and it will go into the solvent without forming any new phase. So, first of all, the solid solubility limit is the maximum amount of solute that can dissolve in a solvent at a given temperature and pressure to form a homogeneous solid solution. If you add beyond that solubility limit, the excess solute will precipitate out or form a separate phase. So, some solutions have a upper limit of solubility where some have the complete solubility range. For example, in the copper zinc system, copper can dissolve a maximum about 40% zinc at higher temperatures. Gold, silver, it can dissolve each other in any proportion, forming a complete solid solution across the entire composition range. These are what are known as the isomorphous system. So, they have the similar structures and very similar atomic sizes. So, we will see these rules also very shortly. So, these solubility limits are influenced by atomic size, electronegativity, crystal structure, temperatures, and so on. So, Hume-Rothery rules, which are named after Sir William Hume-Rothery, they provide a set of guidelines that help predict when two metals will form a substitutional solid solution. These are crucial for understanding the solubility of one metal in another and for designing the alloys with the desired properties. So, the first is that atomic size difference between solute and solvent must be less than 15%. So, R solute minus R solvent by R solvent should be into 100 should be less than 15. Then solute and solvent should have the similar crystal structure and similar electronegativities and similar valency as well. If the valency is different, then a lower valency metal will dissolve more of a higher valency metal, while a higher valency metal can only dissolve a limited amount of a lower valency metal. So, just to give you an example, for instance, if you see copper nickel, the atomic size difference is very less, which is 2%, whereas in the copper lead it is a 36% difference. So, these are in favor of solid solution as per the Hume-Rothery rule. These are not in favor, and you can see this in the phase diagram also. Copper nickel, you have a isomorphous phase diagram, whereas a copper lead, in fact, it has a monotactic kind of a phase diagram. Again, crystal structure also, copper nickel both are FCC. Copper zinc, if you see that copper zinc, although the size difference is not that much, but the structure, copper is FCC, zinc is HCP at lower temperature. So, you see the copper zinc also has a solubility range, but it is not a isomorphous system. Electronegativity of copper and nickel are again similar, 1.9. For copper lead, it is very different. So, that is why you see much more, you see no phases are almost like a phase separation here. And valency for copper nickel both are 2. For zinc and copper, you see this interesting case where we saw the last Hume-Rothery rule about the valency. So, copper is +1 and +2 both, zinc is +2. So, what we saw is that copper is +1, so it can dissolve more of zinc. That is why you see a higher solubility of zinc in copper, whereas the reverse is not true. The zinc does not dissolve that much of copper. So, here you do not see any significant solubility. So, with that background about the solid solution, about the interstitial and the substitutional, let us see some more key trends or key features of the solute diffusion or the impurity diffusion in the metallic alloys. So, I hope you are clear with the distinction between impurity and the solute. As such, you can call both as solute, but impurity is typically are the solutes which are less than 1% and which are undesired, which you do not want primarily in the system, whereas solute, when you say that solute is something that you intentionally add. So, we call for example, the impurity diffusion coefficient as D2 and self diffusion coefficient as D. So, this actually should not be D1, because in typical convention we so this is only D. So, the D2 it lies in a narrow band around self diffusivities. The D of solvent atoms typically between 2 by 3 Tm, D2 by D is somewhere between 1 by 100 to 100 in the temperature range of 2 by 3 Tm to Tm. And the activation parameters also you can see that the D naught lies very close, so 0.1 to 0.10, 0.1 to 10, and the activation energies are also between 0.75 to 1.25 EVs. Sorry, not EV, this is a ratio, so it is dimensionless. The ratio lies somewhere between 0.75 to 1.25. So, diffusion of substitutional impurities. So, remember we talked already a little bit about the interstitial diffusion in metals. So, we are talking here more about the substitutional impurities. So, that occurs by the vacancy mechanism. So, the theory of vacancy mediated diffusion, you know that it involves that the probability of vacancy occupying a nearest neighbor site of substitutional impurity also has to be taken into account. So, whenever we talk about the vacancy mechanism, the finding a vacancy has a certain finite probability which is much less than 1. So, that also has to be taken into account, and that is written as this expression, equilibrium concentration into exponential Gb by kBt, and here it is the written separated into entropy and the enthalpy terms. So, unlike the self diffusion in pure matrix, several atom vacancy exchange rates need to be considered. For example, we saw the 5 frequency model for FCC and the 4 frequency model in BCC when we were talking about the correlation factors. And the impurity correlation factor is not just the function of the lattice geometry, but also depends on the various jump rates of the vacancy. So, that is also has to be taken into account. So, for example, we see that the vacancy correlation factor F2, the impurity correlation factor F2 is written as omega 1 plus 7 by 2 F3 omega 3 divided by omega 2 plus omega 1 plus 7 by 2 F3 omega 3. Just to remind you, these are the meanings of these omega. This we saw when we were talking about the correlation effects. So, where omega 2 is the solute vacancy exchange rate, omega 1 is rotation rate of the solute vacancy pair, omega 3 is the dissociation rate of the solute vacancy pair, omega 4 is association rate of the solute vacancy pair, and omega is the vacancy atom exchange rate in the solvent. So, the correlation factor, it also depends upon these exchange rates. And F3 is the escape probability, which is a function of omega by omega 4 and the ratio of omega 4 and omega 3, which are solute and solvent. So, association and dissociation rates, they vary as exponential Gb by kT, where Gb is the binding energy of the solute vacancy pair. The impurity diffusion coefficient D2 therefore can be written as F2 A square nu naught exponential in the diffusion entropy term, and in the enthalpy activation enthalpy term you have now several contributions coming, not just the vacancy formation and the migration, but also the binding energy of the vacancy and solute. So, when vacancy and solute interact with each other, there is a certain amount of energy you can say released or gained by the system. System lowers the energy a little bit. So, that's why it enters as a negative term. And similarly for the activation enthalpy as well, you have a minus binding energy term coming to picture, the enthalpy of binding. So, the activation enthalpy for the impurity diffusion by vacancy mechanism. So, remember again, when we talk about impurity diffusion, impurities can be substitutional as well as interstitial. So, last video we talked about interstitial impurities like carbon, nitrogen, hydrogen, oxygen. Here what we are talking about is substitutional impurities. So, in the substitutional impurities, because the vacancies are involved, so there is a formation of vacancy term coming into picture, the binding energies are coming into picture, whereas in the interstitial case we saw that only the movement is through the interstitial. So, there is no defect formation term that comes into the equation. So, the activation enthalpy has this term which is vacancy formation energy, the binding energy is subtracted, migration enthalpy, and additional term C, which takes into account the correlation factor dependence on temperature. So, the ratio of impurity and self diffusion coefficient, if you calculate, it depends upon d2 by d is equal to f2 by f into omega 2 by omega into omega 4 by omega 3. And the difference in the activation enthalpy for the solute diffusion or the impurity diffusion and delta H is the activation enthalpy for the lattice diffusion or self diffusion. This is equal to minus Hp plus H2 m minus H1V m plus C. Now, there are certain theories put forward to explain this difference, and one of them is the electrostatic model. So, in the electrostatic model, what is proposed is that delta Q is proportional to the valence difference between the solute and the solvent. So, the solute and the solvent valence difference contributes to the difference in the activation energy. Impurities with higher valency than solvent, they attract vacancies, and the lower activation enthalpies are therefore found for their or the lower activation enthalpies they have than the self diffusion. So, wherever the impurities have the higher valency, they tend to attract the vacancies, and therefore, their lower they show the lower activation enthalpies than the self diffusion activation energies. So, in the model proposed by Lazarus and which was further refined by Leclerc, it was assumed that the excess charge, the delta ZE, is responsible for delta Q, okay, where vacancy is assumed to carry a charge minus Z into E, and the impurity carries a charge Z2 into E. In the Thomas Fermi approximation, the exchange charge of impurity results in a perturbing potential, which is given by alpha into delta Z into E by R exponential minus QR, where 1 by Q is known as the screening radius, which is independent of delta Z and can be calculated from the Fermi energy of the host. And alpha is a dimensionless screening parameter which depends upon Z. Now, Hb, we saw that it is the electrostatic energy of the vacancy located at a nearest neighbor distance d of the impurity. So, for the calculation of this difference, the migration term between the solute and this is the migration term for the mono vacancy, the Leclerc proposed a saddle point configuration where you have the two half vacancies located on two neighboring sites, and each half vacancy carries a charge ZE by 2. In several solvents, this electrostatic model was found to be useful. The delta Q is proportional to delta Z. If delta Z is positive, then impurities diffuse faster. If delta Z is negative, then impurities have been shown to diffuse slower. So, for example, solvents noble metals, zinc and cadmium follow this behavior. For transition metal solutes in noble metals and for other solvents such as alkali metals, divalent magnesium and trivalent aluminum, electrostatic model does not agree so well. Possible limitations are that screened Coulomb potential may not be a suitable choice for some solute-solvent combinations. There is no effect of atomic size in the electrostatic model that is taken into account, and it only talks about the delta Q but not the pre-exponential factors. So, these may be cases, this may be reasons why it is not applicable to other systems. So, now a few words about impurity diffusion in aluminum. Aluminum, as you know, it's a very important metal, especially in development of lightweight alloys and lightweight materials. Also, it offers resistance against oxidation. So, a lot of places aluminum finds its application, one of the most widely used metals. So, let us see a few features about aluminum diffusion. So, we know that it is a FCC structure, it is a trivalent metal, and the most of the transition metals have extremely low diffusivities compared to aluminum self diffusion, like vanadium, titanium, copper, manganese, iron. They all have diffusivities which are less than self diffusivities of aluminum, and consequently they have higher activation enthalpy, which is in fact different from that predicted by the electrostatic model, and have a high pre-exponential factors. When it comes to non-transition elements, the diffusivities are similar or slightly higher than the self-diffusion of aluminum. Pressure effects have also been studied in the case of impurity diffusion in aluminum, and for zinc and germanium, an activation volume of around 1 omega, which is similar to that of aluminum, has been found out. And for the transition elements like cobalt and manganese, slightly higher activation volume in the range of 1.67 to 2.7 omega has been estimated. And here the difference between the transition metal and the non-transition metal diffusivities in aluminum come from the difference in the vacancy impurity interactions. Then there is something called as open metals. Open metals is just a notional term used for solvents that permit fast diffusion into them, and these indicates the large ratio of the atomic radii of the solvent and the solute. The classic example is gold, platinum, palladium and nickel group elements. They have very high diffusivities in lead, which are 3 or more orders of magnitude faster than the self diffusion. Fast diffusion of 3D transition metals is also observed in some other polyvalent metals like indium, tin, antimony, titanium, zirconium, hafnium, and for noble metal diffusion in Na. Noble metal solutes are fast diffusers in tin and in indium and thallium. So, the question is this, when these elements which are supposed to be, that is why I said that this term interstitial and substitution is sometimes relative. So, this fast solute diffusion, then the question is that occurs by which mechanism? If it occurs only by interstitial mechanism, but the radius ratio is still relatively large, for example, Ra by Rag by Rpb is approximately 0.83. So, this is still large to believe that all the solute goes into only the interstitial side, because it will cause so much of strain in the lattice. If you say that it is only vacancy, but then the diffusivities are too high to have achieved this by only vacancy mechanism. So, therefore, what has been understood is that the fast diffusion in open metals is attributed to the dissociative mechanism. These solutes, they act as hybrid solutes which are distributed over interstitial sites as well as the substitutional sites. These are indexed Bi and Bs. And if the local equilibrium is established, then the law of mass action says that Ci into Cv by Cs is equal to Kt, which is equal to Ci equilibrium into Cv equilibrium by Cs equilibrium, where Kt is the temperature dependent constant. And the effective diffusivity of the solute can be written as d effective is equal to di into Ci equilibrium divided by Ci equilibrium plus Cs equilibrium plus dV into Cv equilibrium by Ci equilibrium plus Cs equilibrium. These are di and dV are the diffusivity of solute, its interstitial state and of the vacancy solid complex. This product Ci equilibrium into di is much greater than dV equilibrium into Cv equilibrium. Then basically d effective can be written as di into Ci equilibrium divided by Ci equilibrium plus Cs equilibrium. So, remember, Ci equilibrium and Cs equilibrium denote the equilibrium concentration of the solutes on interstitial and the substitutional sites. If Ci equilibrium is much greater than Cs equilibrium, then you have effective diffusion coefficient as Di. If Cs equilibrium is much greater than Ci equilibrium, then effective diffusion coefficient is Di into Ci equilibrium by Cs equilibrium. The ratio of this is equal to exponential minus Gi by kBt, where Gi denotes the Gibbs free energy of forming an interstitial solute from a substitutional one. Then these solute and solvent diffusion in alloys, the D star A XB. So that means how much the when you add a solute, how much the solvent diffusion coefficient is changed. So that is given by dA star into exponential B XB, where XB is the fraction of the solute. If the solute fraction is very less, say less than 1%, then the solvent diffusion coefficient can be written as dA star XB is equal to dA star 0, where dA star 0 is without any solute. And if you expand this, it is right 1 plus B1 XB plus so on. The B1 XB accounts for the change in jump rates of the solvent atoms neighboring the solute atoms. So that means if a solute is present near to the solvent, so how the vacancy exchange rate of solvents are changed, that is what is captured in this product B1 XB. Quadratic terms correspond to the effect of pairs of atoms. This B1 is also known sometime as linear enhancement factor. In the alloys, the solute diffusion coefficient can be written as dB star XB is equal to dB star 0 plus 1 plus B1 XB plus so on, where dB star 0 is the solute diffusion coefficient for infinite dilution and B1 expresses the influence of solute-solute pairs. Again, if you use the 5 frequency models for FCC solvents, you can arrive at the references, you can arrive at the expression for B1 as suggested in these references, and it is seen that the B1 depends upon the atom solute vacancy exchange rates plus the partial correlation factors xi, xi1 and xi2, and a term of the binding energy as well. So with this we end our discussion on the diffusion in the metallic alloys. We'll continue discussing more systems of interest in the upcoming videos. Thank you.